Let's dive into the revolutionary transformer architecture that changed AI forever. The transformer uses attention mechanisms to process sequences, allowing every part of the input to directly connect with every part of the output. Before transformers, sequence models had serious limitations. RNNs process words one at a time in sequence, which is slow and makes it hard to capture long-range dependencies. Recurrent networks must process each token one after another, preventing parallel computation and slowing down training. Information from early tokens gets diluted as it passes through many sequential steps, making it hard to connect distant parts of a sentence. The key breakthrough is self-attention, which lets every word attend to every other word simultaneously. In self-attention, every token can directly look at every other token, creating connections between all positions in parallel. The attention formula computes how much each word should attend to every other word using queries, keys, and values. Let's break down how the attention mechanism actually computes its output. Each word is transformed into three vectors: a query to ask what it's looking for, a key describing what it offers, and a value containing its information. First, we multiply the input by three learned weight matrices to create queries, keys, and values. Next, we compute similarity scores by multiplying queries with all keys, showing how relevant each word is to every other word. The scores are computed as query times key transpose, divided by the square root of the key dimension for numerical stability. We apply softmax to convert scores into probabilities that sum to 1, determining how much attention to pay to each word. Finally, we multiply these attention weights by the value vectors to get a weighted combination of information from all words. Instead of one attention mechanism, transformers use multiple attention heads in parallel. Multiple attention heads run in parallel, each learning to focus on different aspects of the relationships between words. The outputs from all attention heads are concatenated and projected to create the final multi-head attention output. Different heads specialize in different patterns. Some might focus on syntax, others on semantics or long-range dependencies. Now let's see how attention fits into the full transformer architecture. The transformer has an encoder that processes the input and a decoder that generates the output, both built from stacked layers with attention. The encoder consists of 6 identical layers, each containing self-attention and a feed-forward network. The decoder also has 6 layers, but adds masked self-attention to prevent looking ahead and cross-attention to the encoder output. Since attention has no inherent sense of position, we must add positional information. Positional encodings use sine and cosine functions at different frequencies to inject information about token positions into the model. The positional encoding formula uses sine for even dimensions and cosine for odd dimensions, creating unique patterns for each position. The transformer architecture solved major problems in sequence modeling. Transformers enable parallel processing, train much faster than RNNs, and achieve better accuracy on translation tasks. Unlike RNNs, all positions can be computed simultaneously, dramatically speeding up both training and inference. Every word can directly attend to every other word regardless of distance, making it easy to capture long-range dependencies. The original transformer achieved record-breaking results on machine translation, beating all previous models. Let's recap the key insights from Attention is All You Need. Self-attention allows every token to look at every other token, computing relationships between all pairs simultaneously. Multiple attention heads running in parallel allow the model to focus on different types of linguistic relationships. By eliminating sequential processing, transformers train faster and achieve better results than recurrent architectures. The transformer architecture became the foundation for virtually all modern language models, powering systems like GPT and BERT.